Hello everyone and welcome to the fifth lecture of solid-state chemistry. In this lecture we are going to discuss superconductivity and lasers. So we go to more advanced applications of solid-state now that we really have all of the background that we need. The lecture is going to be divided in three parts, so three sequential videos that you need to watch in a smooth sequence. In the first one, we are going to talk about the principles of superconductivity, from the discovery to the explanation. And in the second part, we are going to discuss high temperature superconductivity and additional applications that you can have of superconductivity as a thing. And then the third lecture is going to be separated, is going to be about lasers material, so different topic from superconductivity. You can follow the progress of the overall lecture on the bar, and the whole ensemble of these slides is available on Canvas as part of the feedback route interactive document. Now, just to start off, we know that the conductivity in any material is given by this equation that relates the number of carriers that usually you want to be electrons, but they could be something different, their charge, which in electron is a negative single charge, and their mobility in the material. Remember, this is a mobility, this is not a chemical potential. Now, when we want to know the number of electrons that we have going around, we need to relate this to the band gap as a thing. So in a metal, which you see over here, the number of mobile electrons is basically constant, but their mobility decreases with increase in temperature. So the net effect is that you will have, as temperature goes up, the conductivity goes down, but not of much, but you can see this effect over here with log of conductivity over 1 over T. In a semiconductor, instead, the number of mobile electrons is very small, but it can be increased depending on how do you bridge the gap. So you can increase the number of carriers by increasing the temperature, so you promote more electrons to the conduction band, or you add it with impurities. So the first, so a lower temperature, you have this distinguish point between intrinsic and extrinsic semiconductivity, and depending then on the number of carriers that you normally generate, at some point, if you keep increasing the temperature, you will get a bridging point in which the conduction is dominated by temperature generated carriers. So with increase of temperature, the conductivity can go up a lot. So you can see this is order of magnitude of conductivity rising. In an insulator, instead, the only difference from a semiconductor, as we know, it's the magnitude of the band gap. So if this band gap is way too large to ever be bridged, the activation of the carriers is incredibly high, so there is no temperature that you can feasibly reach for which you will have a significant amount of conductivity. So if you increase the temperature a lot, you start to have some conductivity, but you can see that this is a completely different business. So our best conducting material, which is not a surprise, are metals. But so what happens in metals when you actually look at the effect of temperature? Now, every conductivity has an inverse, which is the resistivity. So either you can plot how easy it is to conduct the carriers, or you could plot how difficult it is to conduct the carriers. So if the difficulty is low, then the conductivity is high. So our thing is that we want to delocalize our own electrons going around. So the metals are excellent because they don't have a band gap, right? But the restriction there is going to be how much electrons are actually able to go above the Fermi level at a given temperature. So for every number of carriers, you have a limited amount that will go up. It's not that you can like freely excite all of them above. They stay restricted there. So you have this small change with temperature. All things considered, you can see that this is not a very huge number of change. But when you look at this feature, the high temperature profile is material dependent. Clearly, you have a series of noble metal here. It is clearly material dependent. It changes depending on the material. But if the temperature doesn't vary too much, so if you are in a sensible range, you could just do a linear approximation, which is this thing that you see here. So imagine if I give you a segment between like this at 1000 and 1400, it could be easy to just plot a line interpolating with these parameters. If you want to do the whole thing from like 200 to 1400, you could see that yes, it's almost linear, but you sort of have this deviation. So if you want your best plotting, you might want to have to change this alpha, which is an high temperature dependent coefficient, which could change depending on the region of temperature. So it's better if you keep yourself in segments. So the resistivity of a metal increases with the temperature. The question, of course, begs of like what happens down here, because this is going towards zero, but going towards zero is not like telling us it goes to zero. So first of all, what is this business up here? What is our problem over here? So our problem here is that when you are at high temperature, in theory, the free path that your electron can have, so how much space your electron can actually cover without hitting something else, should be several hundreds of the atomic spaces of your material. So you should have a lot of capability of going around. But at some point, there will be another effect of collision, which is a collision with a thermal lattice vibration. Now, the vibration of the lattice as a function of temperatures are called phonons. And a phonon in itself is a quasi-particle, because we keep using that duality of if it's a wave, it's also a particle. And why is this a wave? Because it's a collective oscillation of the lattice. It's not one point oscillating without any correlation with the other point. By nature of having the solid state, when you move an atom, they will want to all move together in reaction. So this thing that you see here is the depiction of an oscillation. You can see that it's not just this atom moving however it wants. When you start moving them, you move them all together. So this thing is like a sort of like an elastic, it's like oscillating a spring, and you can imagine your bond as the spring and your atoms as the weight on the side of the spring. And they tend to have either longitudinal or transversal direction, so they're just oscillation. But since they are quantized, they are also like quasi-particles, so they're a quantum of lattice vibration. They're unavoidable. If you give temperature to your lattice will start to vibrate around the position. So for every structure that we've ever seen, you always have to consider that those atomic positions are sort of like the average atomic position. Depending on the temperature, your atoms will oscillate in an harmonic way, which gives you these quasi-particles. Now the issue is that so this thing is the reason why your material has a heat capacity, and it comes with the internal energy of your lattice, so very nice and smooth. But since these are particles or quasi-particles, but even if you imagine just the waves, these things are prominent at high temperature, and they become something that your electron can actually hit. So the collision with a phonon, so your electron is trying to sweep around this structure whole happily and just conduct, go somewhere else where it feels the lower potential where you can actually end up to. But as it's trying to go through in its free path, at some point it might hit a lattice vibration. If it hits a lattice vibration, that electron is stopped in its track. So that thing is the reason why you stop, like you have a high resistivity at higher temperature, because the thing that is giving you the resistivity at high temperature is the fact that your lattice is vibrating. So for high temperature, we're fine. Now, at low temperature, we know that as you approach 0 Kelvin, you should approach your limit in which your conduction band is completely empty and your valence band is completely occupied up to the Fermi level. And in theory, the distribution of electrons that you go and that you have up, this is another plot in comparison to the one that we had in lecture 1, but it's plotting the same thing, just giving you a sense of what temperatures do we have to work with. So if this is your Fermi level, in theory, at 0 Kelvin, this is completely occupied and this is completely empty. You can see that this is the distribution at 500 Kelvin. So this is already higher than room temperature. So this tiny fraction will be empty in valence band, and this tiny fraction will be full in conduction band. So for any sensible temperature, the amount of electrons that you have going up is tiny. And if you lower the temperature, this thing will get closer and closer and closer to a step function. The only thing that gives you the metallic conduction is this fraction of electrons that go into the conduction band. So if you go close to 0, and this number of electrons, if you go close to 0 Kelvin, and this number of electrons goes close to 0, so the population up here is almost 0, then are we saying that we have 0 conduction, therefore infinite resistivity? That could be a question. Consider that, of course, when you are at 0 Kelvin, that vibration of the lattice should be frozen as well, because those are temperature dependent, so you should have fewer phonons. But if you don't have electrons to conduct, what do we do? This question clearly cannot be just solved at theoretical level. You actually need to go close to 0 Kelvin and measure the conductivity of your material, which begs a completely different question, which is how do you get to 0 Kelvin? To 0 Kelvin, the first approach that you probably already know to lower the temperature is usually liquid nitrogen. Liquid nitrogen was an improvement of the late 1800s, when they sort of figured out a way to first separate the nitrogen from liquid air. And the trick is that air, to begin with, was not considered to be something that you could liquefy, because if you can liquefy it, then you can separate the components. But the constituents of air were known as permanent gases, so just by compression you cannot liquefy them. Given that thermodynamic is a thing, if you do compression, expansion, compression, expansion, and meanwhile you're cooling your system with different ways, your system will cool more than you're actually considering. So consider this concept that we can discuss later. So if you compress your gas, the temperature will rise, but you're externally lowering the temperature by having a cooling system. So you compress your gas, you cool the compressed gas. Then you let the gas expand, but you already cooled it, that will go lower in temperature. Because expanding a gas cools the temperature, you already removed the additional temperature. This means that your gas will go to an even lower temperature. This thing is the thing that gives you the possibility of liquefying components of air, and liquefying in particular nitrogen. So the boiling point is 77 Kelvin, which means that you can go to around minus 200 degrees, because you're using the fact that this will have an evaporation. So when it's liquid, anything around it will get the temperature dropped at minus 200 Kelvin. Sorry, minus 200 Celsius. The limit usually operational is that you cannot use liquid nitrogen for any temperature that is lower than 85. You're really pushing it. You can try 80 Kelvin, but it's only if your system is really good at the job that it's doing. Otherwise, 77 is not really achievable. Now this you can cool your system with liquid nitrogen and then measure the conductivity. Tiny problem, the conductivity in this region is still linear with temperature. So whatever, this is not our answer. You still see that increase and you call it a day. So this is already too high of a temperature to see what is going on at 0 Kelvin. Which leads us to our second point, which is liquid helium, accidentally a Dutch discovery. This was at Leiden University, so nice stuff. So the trick there is that if you manage to liquefy helium, mostly same process, you can get to as low as 1.8 Kelvin if you're really pushing it. Usually you call it 2 Kelvin is the temperature of evaporation of helium. Why is it so low? Because helium is a noble gas. You can only get it to liquid. To get it to solid, you will have to compress the liquid, so keep it at very low temperature and incredibly high pressure. Otherwise the maximum that you can gain is actual liquid helium. If you want to supercool your system, there is a point in which helium-4 and helium-3 are not completely miscible, and there is this thing that is called dilution fridge, in which if you manage to separate helium-3 and helium-4, then one of them is going to bring you to even lower temperature. Now this is reasonably close to 0 Kelvin that you can actually start to do business. So if you measure your conductivity using liquid helium with a metal, you can see that as you start going above 50, then you start to see the linear behavior. So this is the reason why using liquid nitrogen will not make the cut, right? When you go to very low temperature, instead of going to 0, you kind of plateau. You can see that these are like in a region between 4 Kelvin and 300 Kelvin. You end up with this plateauing region up to like 25-ish, more or less. So this value depends, this is like the residual resistivity of the material. So there is a steady level of conductivity under which you do not go. So that's the limiting conductivity of your metal. This depends on the type of the metal and on the purity of the metal and the thermal history of this thing. So this thing is a concept that correlates to the fact that we said that it's impossible not to have defects. So it doesn't matter that you have incredibly few electrons above the conduction band, you're going to have defects in your material. The defects are going to give you a limiting amount of carriers. The limiting amount of carriers, which is the residual that you keep at low temperature, is the thing that is going to conduct electricity. So depending on the material, the sample history and the purity, you end up at this plateauing level. But given the fact that you had this thing of issues with purity, thermal history, if you wanted back in the days, like early 1900, to do a measurement of an incredibly pure metal, you should use metals that are easy to purify. Otherwise you end up with like measuring the same metal with a different sample history, different purity, and I always get different results. This is not particularly nice for any physical chemistry type of measurement. So platinum and gold and mercury were the easiest thing to purify. Mercury in particular because it's often liquid at higher temperature, so it's easier to purify away the impurity. Now, our guy over here at Leiden did this measurement with mercury, and in the 1911 he noted that when you cool below 4.2, so this is hardcore liquid helium temperature, the resistivity of the system drops to 0. So you can see this whole school type of plot, so like literally taken manually drawn by hand, but you can see that below this point any other thing that he collected, any other point that he collected was a 10 to the minus 5 ohm of resistivity. So this is telling you that your material fundamentally does not have a resistivity. This is marked as the discovery of superconductivity. Nobel Prize in Physics, 1913. Nice. So in early days of the superconductivity, there was this like huge discovery of like, okay, let's measure every metal, basically any metal alloy something, and see what happens when you bring it to very low temperature. And a solid will act as a superconductor if it can conduct electricity without any resistivity below a certain critical temperature, implying that whatever current you try to run through your system will just go indefinitely. So from mercury at 4.2, then they did a series of other measurements and discovery. So higher values of TC after the first one, in some cases even lower, so tungsten and lead and niobium, they all have this series. There are also intermetallic compounds, alloys, other things, so mixture of metals, all have superconducting values between 10 Kelvin and 23 Kelvin, so still liquid helium temperature. Remember that this thing can be lost and gained with temperature and field, so this is reversible. So you could put temperature and your material will lose the superconductivity, you cool it back again. This is also magnetic field dependent. There is a degree of periodicity in how these atoms actually behave, but remember that stuff like iron, cobalt, nickel, copper, silver, gold, things like that do not display superconductivity. So in that case you end up with the residual amount of conductivity. And it was observed that ferromagnetism and superconductivity tend to not coexist. So if your material is ferromagnetic, it will not be superconducting. So this was already a discernment that was obtained in the early days. When we say that this thing is field dependent, we mean that if you apply a magnetic field to your material and this magnetic field exceeds a certain critical value, then the material will just lose the superconductivity. It was also observed that there was a correlation between the magnitude of the applied field and the temperature in comparison to the critical temperature of the material. So this is a series of parameters that you use to correlate your whole business, right? Interesting point is that superconducting material exhibit a perfect paramagnetic behavior, and this thing is called the Meissner effect. So they behave like a perfect paramagnet. As we were discussing last week, like diamagnetism tends to just dissipate and make less dense any line of field that go through your material. But the issue is that this is usually kind of useless. It's just something that happens and just happens because of the reaction of your electrons to the magnetic field. But your superconductor actually does something interesting. It's a complete, perfect diamagnetic effect. It's 100% diamagnetic. The field does not penetrate inside the material, not beyond a certain penetration. So this penetration depth is called the London penetration depth, and this relationship, if you actually want to derive it, requires considering the Maxwell equation. And the idea is that the field will start to penetrate inside, but since the material is a perfect conductor, this thing will kind of like generate a very local magnetic response and a circulation of current, but the current density that is generated from inside of the material will increase if you keep penetrating inside. So you kind of create a shielding point. So beyond this London penetration depth, the penetration of the magnetic field is actually blocked. You cannot go any further because that will just get you repelled. So this means that the magnetic line of fields just get pushed away from the material. This penetration depth is usually around 100 nanometer. So this is super, super, super tiny, like a layer, couple of unit cells of your material and nothing more, and your material could be an entire block of something. This is the reason why this thing kind of floats. And beyond 100 nanometer, the strength becomes negligible, so it's as if there is nothing. In a normal metallic state, you will have normal penetration of the magnetic field and an induction that follows. In the superconductive state, your material is perfectly diamagnetic, so it will just repulse any magnetic field that you try to put onto it. This will beg the question, how do we explain this behavior? And this was a big deal, explaining the superconductivity not as an experimental thing, but where does it come from? It's a natural big question. So we know that we have these electrons that are delocalized. So your material is metallic usually. All this material that we see behave like a superconductor at low temperature. At higher temperature they are metallic. So you start with this delocalized arrangement in which the electrons are free to go, and they might very well collide with either phonons or other imperfections, defects in the lattice, and give you this residual resistivity. This resistivity will increase with temperature, usually linearly, as you go beyond something like 50 Kelvin. So most of the superconductor that we listed have this thing of, okay, at the critical temperature combined with the critical field, we switch the superconductivity in. These three guys that modeled the superconductivity behavior are the responsible for the thing that we call BCS theory of superconductivity. They won the Nobel Prize for this thing because before, as you can see the date, this is 1972, meaning that for several decades everyone could measure superconductivity, no one will know what was going on. The reason why this thing is particularly impressive and it won them the Nobel Prize is that it gives an approximation that is basically a quantum mechanic many-body behavior model for the metal. So it considers the many-body approximation, meaning all of the electrons and all of the phonons, everything that is going on. It gives a unified theory. So this theory is not only theoretical, it's also correlated to a ton of experimental proofs collected, because otherwise it wouldn't make any sense. They developed it on the basis of what we could see from the experimental point of view. So one of the very first steps, we're going to give 3 proofs of what is going on that leads to the actual description. The first step is that there must be a band gap that separates whatever is going on in the superconducting state, so whatever is conducting electricity as a supercurrent in the low temperature regime, to the normal state of conduction. Why? Because they must have a different behavior. So if there were to be electrons, then they should behave like electrons, and we know how electrons behave. They should go with the normal conductivity. But there is a critical temperature and a critical magnetic field. When you have these two behavior, you usually imply that you are jumping a band gap. So there must be a limiting level of energy required to move from one state to another, which you see for a lot of other things, like even semiconductors. You know that you will have a critical temperature below which your material is not really conducting electricity. In the same way, you know for magnetism, you have a critical temperature from which you don't have the magnetic ordering. This must be the same thing. We're changing behavior. So this band gap is usually suggested not only by the fact that you have the critical temperature and the critical field, but it's suggested by stuff like the specific heat. Now, materials like vanadium, you can measure upon warming towards the critical temperature. So your material is superconducting, you are warming towards the critical temperature. The heat capacity of vanadium, that has a critical temperature of 5.4 Kelvin, increases as you approach 4 Kelvin. And this is not a small increase, this is like 100-fold increase in heat capacity. This exponential increase in heat capacity means that all the thermal energy as you approach the gap is being used to bridge that gap. As the temperature increases, you have this exponential number of particles that can actually go through that gap and bridge it to go to whichever other state. So there must be a band gap, and the band gap is proven. Second point, so this might be a particle that is jumping some sort of gap that we don't expect to be there, because your material should not have a band gap being a metal. But since your material is not behaving like a metal, it must have some sort of transition. The transition implies the bridging of the gap. Other very important business is what is going on in terms of the carriers. Because if the electrical conduction of stuff like mercury, or like mercury is particularly useful because it has a lot of isotopes, but every one of these, if the electrical conduction were to be purely electronic, then it should be completely independent of the mass of your material. So whether you have mercury in one isotope, the other isotope, a mix of the isotope come from the number of neutrons in the nuclei. So if the conductivity is purely electronic, then it shouldn't make any sense for the conductivity to be dependent on the mass of the isotopes. And instead, with materials like mercury, for which you can actually control the isotopic quantity, so if you isolate the different isotopes of mercury and measure the transition of superconductivity, you can see that there is a clear dependence. So your superconductive temperature is basically a function of the isotope mass. You go at higher superconductivity temperature as the mass of your isotope decreases. So this thing is like a function of almost beta to the 0.5. So this is a very interesting behavior. This is telling us that this cannot be a purely electronic effect. The thing that is affected by the isotope mass is usually the vibration of your material. So all of those phonons will have a different behavior depending on how heavy are your atoms. Because if you imagine the spring, if you change the weight at the side of the spring, even if the strength of the bond is the same, the vibration will be different. So these harmonic quasi-particles will behave differently. So if the critical temperature is changing, is because the environment must be using this energy in different kind of way. The electrons don't care, so there must be a coupling between something that the lattice is doing. Now there is a final point of evidence that correlates to the first and the second, is that if you have this gap, you should be able to measure the gap. Now the effective effective energy gap in the superconductors can actually be measured with microwave absorption experiments. So in the same way with photovoltaics, we are concerning ourselves with how do you bridge the gap with visible light. In this case, if the gap is much smaller, you measure with microwave absorption experience. And it is clear from the plot that we have that the gap decreases as you approach the critical temperature. So there must be a sort of collective nature of whatever is going on. So the charge carriers that you have must consist at least of two things that are bound together, and this binding energy, so our connection between these two things that are correlated with each other, is weakening as you approach the critical temperature. So this is the reason why the gap decreases, and the gap that you measure as you approach the critical temperature tends to go to zero. Above the critical temperature, there is no connection among this double particle behavior, and your material behaves like a metal. So something, meaning that it will go to a zero band gap. Whereas when you go lower and lower and lower, below the critical temperature, you have a stronger and stronger and stronger and stronger connection between whatever is going on in this two-body behavior. So once again, the single electron must be eliminated from this thing. You cannot get an energy gap with something like electrons. All available states up to the Fermi level must fill up, and you have no other options because these things have spins. They are fermions, meaning that they have a different series of quantum numbers. You cannot put multiple electrons in the same energy states and get a gap. The transition that you have going on towards the critical temperature, and you see the transition to superconductive state, it's thermodynamically second order. So you see no discontinuity in enthalpy and in entropy as you go to the critical temperature, but you see a discontinuity in the first derivative. So the first derivative of enthalpy in comparison to temperature is actually the heat capacity. And we saw with vanadium that you have this huge change in heat capacity as you approach. So when you cool at the low temperature superconductive states, you have more and more and more order of whatever is going on down here, and this small band gap. The fact that you can measure this band gap with microwave absorptions, it tells you that this gap should be around 1 micro electron volt. Note that this is about like an order of magnitude, like 3 orders of magnitude lower than the band gap in a semiconductor that absorbs visible light. And in a second order phase transition, everything occurs over a wide range of temperature. It's not a snap moment of either in or out. You have a smooth transition, and these changes are complete, like they are complete when you go very much down, and at the transition temperature they just disrupt and they become non-existent. So instead, if the transition were to be second order, it would be from 0 to 100 in a second. You just snap and make this a complete perfect transition. This doesn't happen, so it must be a gradual interaction that increases as you go below the critical temperature. Nice. So what is the answer? The double particle here is this mixture that is called the Cooper pair. So the idea of the BCS theory is that the resistance-free conduction is achieved with a pair of electrons. It's not a single electron, it's 2 electrons together, and these couple of particles, they can be, instead of being a fermion, so with spin up, spin down, 2 completely different energy states that are independent of each other. They can have a single behavior, and you can condense a series of these particles in the same energy states. And the fact that you can have a type of particle that does not behave like a normal electron is the basis of why your material can be superconducting. So what happens when you have this thing? So why can you have two electrons bound together? Is that you're coupling with the phonons. At such a low temperature, when you're passing your electron through the lattice, you start to bend the lattice as it goes. So the first electron that passes bends the lattice. The fact that the lattice is bending creates a reaction on the other side. So there is a positive charge going through that will basically attract another electron. So when you pass an electron, two electrons will actually bound together, because this distortion of the lattice will create a preferential path, so it's easier to conduct two electrons together than it will be to just conduct one and have this weird distortion. So when you manage to move the phonons around in a way that is coupled with the motion of the electrons, you can create a Cooper pair. And the Cooper pair is this pair of electrons that travel together. Since they travel together in a way that is coupled with the lattice vibration, not independent of the lattice vibration, they do not encounter any type of resistivity. So the type of stuff that you have going on is two electrons with a phonon interaction that is mediating their binding, a binding energy that is in the milli-electron volt, meaning that you can measure it when you put microwaves through the system, and a spacing that is like the interaction is around 100 nanometers, so they are far away from each other, but since they are coupled with the lattice vibration, they just go happily. And this thing is uncomparable to the lattice spacing. So this is much bigger, the distance at which they interact with each other because they couple with the phonon is much bigger than a lattice spacing. And it's this binding energy that you have in milli-electron volt below Tc can actually hold them together. Above Tc does not exist. They just disrupt and they go independently of each other. Now this can sound strange, but every point of this description is actually experimentally supported. And the important thing is that the electrons in the Cooper pair must have an opposing spin, so they are coupled with each other antiferromagnetically. So there is a zero angular momentum and zero spin when you actually consider the Cooper pair as a unit bound antiferromagnetically. So you call them a singlet state. So when you bound them together, they don't have like a net moment. This is also the reason why applying a magnetic field, as we know, disrupts the superconductivity. So even if you are below the critical temperature that will be needed to bind these electrons, if you apply enough field, you could just crack them up and break them, and you break the superconductivity. Note that this also gives us the answer as to why you will have no superconductivity in metals that we describe as very good metals. Any metal that is a very good metal is a very good metal because it has a very, very low lattice vibration. If the lattice vibrations are already low, it means that at low temperature they won't be able to be prominent enough to do this type of coupling. And this coupling is the Cooper pair coupling, core of the BCS theory of superconductivity, and it tells us why can you have superconductors. These are all low temperature superconductors. In the next part of the lecture, we are going to look at some high temperature superconductors.